Okay, so let's get started. Let's get back to our lecture. We were just discussing how to derive a possible loss function. So I give you an example. We started with a problem, classical problem in computer vision and some other areas. In computer vision would be, for example, detecting the location of an object, right? So the center point of that object or some landmarks of that object that define, for example, the shape of that object, right? And so on and so forth. And what we would do is we have a network, F, right? This is our regressor, our deep neural network, given the input, which is our image, the ith image, our parameters of the network currently, and the desirable output, right? That's given to us. And what we want to do is compare this with some loss. And if we use the square loss, that would be equivalent to if I have q such parameter, landmarks that I want to detect, then I'm going to say this minus, so fj comes from f vector f1 through fq, right? Which identify each of the functions that map to each of the different landmark points, let's say. And then I have this output for the network, the jth output, and I compare this to the desirable jth output for that sample, the ith sample, right? I squared this. This is a square loss, right? And we know what the problem with this is. The problem with this is that this square loss looks something like this. Whoops. It looks something like this, right? Square loss. And what's the problem with that? Outliers, right? That we're actually focusing too much on the points that are going in this direction, right? So if you are here, 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 maybe about this range, you're fine. But after this, it grows exponentially fast, and that's a problem for us. OK, so what we did is we changed this loss function, and we said, OK, so what we're going to do, we're going to have a function h that returns whatever is of interest to us. So for example, in regression, I say h of fij, it's equal to fij, right? It may just be as simple as that. But in classification, fij will be the output of the network, and it can be a positive number or a negative number, meaning the positive side of the classifier, the negative side of the classifier, right? And if I take h to be the sign of that value, so if it's positive, I go to class 1. If it's negative, to class 2, then I'm done, right? So this h is just a way to change the value of fij to something that we want to. And then I'm going to use the function g, right, to compare two possible outputs of the network with two possible outcomes, right? And the difference between this and this is that here, what we're saying is if these two outputs of the network are similar, so should their desirable outputs. And if they are different, so should their outputs, right? And that difference of the actual output of the network and the desirable output should be the same, ideally, right? So I did the derivations. You can show that you can compute this using any metric, any norm that you want to decide to use. So you can use a p-norm. You can use the whatever norm that, or even quasi-norm that you want to use. But I also showed you that you can define this metric where for a triplet of points, right, GZU, we compute the area that's defined by that triangle. So if I have 3 fiducial points here, right, that defines a simplex, a two-dimensional simplex with triangle, and the simplex is nothing else than a triangle which is filled, right? So you actually measure this area here. And now I'm going to do x minus z cross product x minus u, absolute value. But why stop at 3 points, right? I could use any number of points that I want to. So I can use Green's theorem to extend this to a larger number of points. So if I can get my notes to work. All right, maybe not. Okay, there we go. All right, so what I can do is I can compute G of a vector. I'm going to indicate this now, X vector, to indicate here that my X vector has been, actually let me do it here. This X vector has been rearranged such that xi1, excuse me, xi1 through xit, and I'm going to put a tilde on top of those and a transpose to indicate that these are also vectors, so don't be confused, or they could be vectors or just scalars, doesn't matter, either way, right? But I ordered them in a way that they are ordered in, I think it's clockwise, right? So that they are ordered in this direction, right? So I can start 1, 2, 3, or I can start here 1, 2, 3, but they always have to go clockwise, right? To be able to apply Green's theorem. And then if you have this, then you can compute the area with this equation. 1/2 of the sum k from 1 to t minus 1 of xik1 tilde times xik plus 1 2 tilde minus, let's see, xik2 tilde times xik plus 1 1. And now all this, I'm going to add xit, where am I looking here? T1, I knew there was something wrong, and 1, 2, minus xi1, 2, xit1. Okay. And I've posted in Carmen the paper that has the short derivations, like 4 lines of derivations of how to extend this result using Green's theorem to get this other equation right here, right? But what this is you're just taking, for each of the elements, you're just taking the first, or you start with k equal to 1, the first element of that list that you have ordered, right? And the first value of the x and y coordinates, right, of the image, or UV coordinates, not to confuse with these x and y. So the UV coordinates would be this u, and this would be the v. This would be for the subsequent value, and here's the opposite, right? And that's what Green theorem does, plus the last one compared to the first one, right? That's it. Straightforward, easy to compute, and that leads you to robust results. Okay, again, paper in Carmen, as always. Take a look. But the point and the message I really want to get across here is that whenever you want to design your own deep network or deep learning algorithm, this is one of the main goals of deep learning, right? There are only 2 things, or mainly 2 things that you have to decide. First one is what's the architecture that you're going to use, which we're going to talk next, today's lecture. And the second one is what loss function you're going to do, which is what we discussed in our last lecture, right? So I gave you all the basics to understand the different types of loss functions that you can derive and the different types of optimization algorithms that you would use to optimize these loss functions that we can derive. But at the end of the day, it is you who has to decide how am I going to derive my loss function, and that is going to define your problem, right? You have to define a loss function that specifies the physics of your world. That's what you have to model. You always model the physics of your world, always, right? And that is never going to be given to you. This you just have to derive, right? And be careful what you derive. If it's a continuous value, like here, right, then you want to use the gradient descent methods that we've been talking about for these type of functions. If it's a discrete value, like for example, it could be zeros and ones, or -1, +1, right? Something binary, indicating that this is present or not present, or is that object is not that object, right? And in that case, we have to use this LOVES extension if it's unconstrained, the multilinear if it's constrained, and so on, right? You have to know all these things, not by memory even, but you have to have them in your notes somewhere when you work on these networks, because you have to be cognizant that depending on how or which function you derive as a loss function, you're going to be using some optimization methods or some other optimization methods, right? Okay? So far, so good. Now, there is only one way to get this right. And believe me, employers, when you go out there and try to get a job in this area in machine learning, if they're interested in deep learning, they will know whether you know deep networks or not. Now you have all the theory. Well, almost, right? We have 2 or 3 more lectures. But other than that, you're going to have all the theory. But you have to go home today, tomorrow, and Christmas break, and practice, 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 right? There's no other solution. If you need to rewatch the lectures, we have the lectures online now, right? So you can rewatch them. And it's actually not a bad idea. I would even encourage you, once this semester is over and you have done all the final exams and you have some time, to actually rewatch it from the very beginning. Because now that you have all this knowledge that you have acquired, you can get so much more out of the course, right? And once you have rewatched these lectures, go online, find some other lectures out there that are specific of one topic that you're interested in, and watch those as well, right? Learn, because there is a lot of material here that we cannot cover in a single semester course. Okay. All right, any questions before I move on? Okay, so next topic is architectures. Now, I've already covered architectures in the sense that I have already given you the building blocks, like the Lego pieces that you can use to put them together to build a network, right? You already know the different types of layers that you can have, right? So you just put these things together and you build a network. The problem is if you just do this, it's probably not going to work, right? I mean, 99.9% of the time, it's not going to work, right? So you have to start by knowing what people have tried and what seems to work, right? So this is what I'll briefly describe in today's lecture. Okay? All right. So this is going to be deep learning architectures, or deep networks, you prefer. So let me start with convolutional neural networks, because this is what we covered the most in our previous lectures. And I'm going to start with not the first one. In the slides that I will post in Canvas, you will see that there are other historical networks like the LeNet. They're very powerful for specific or simple problems. But let me start here by talking about a network that I've already mentioned, which is called AlexNet, or people call AlexNet. And that is the first network in recent times that was successfully applied to a difficult problem, specifically in computer vision. So in computer vision, a few years ago, there was this competition that kept recurring every year, which used an image data set that was called Imagenet. Okay. And computer vision algorithms were doing okay on that data. Well, okay, it's a stretch, but they weren't doing too bad, but they were not doing good, right? They were not achieving very good results. And then one year, some people designed this network, and believe me, they were not the only ones trying to do that, right? There were many groups that I knew of at the time that were designing deep networks, trying to make them work on that data set. No one could figure out how, but this group finally managed to do so. And that year, not only did they win the competition, they won the competition by like 8 or 9 percentage points, right? Which was unheard of at the time. Then, of course, that changed everything, right? Then people went like, oh, okay, so this is the network that works. So let's explore a little bit more about this. And as we'll see today, the networks kept getting better and better and better. And now they are, for that particular data set, they are pretty much as good as humans, if not better. Okay? And they're probably slightly better than humans. But that statement has to be qualified. The reason they are better than humans is because many of the object classes in Imagenet are very specific objects, like different breeds of dogs or flowers or whatever, right? And we, general public, are terrible at this, right? So the network makes a lot of mistakes in places where we will never make a mistake, like mistaking a dog for something else, for a horse, say. But we make a lot of errors where the network doesn't, which is identifying the breed of that dog, right? So, but on average, the networks are at least as good as humans on average. Again, the mistakes are not the same. So here is the idea of AlexNet. And when you talk about architectures, it's as simple as saying this. So they just start with a, actually, let me do it here, because otherwise you're not going to see. So you start with a convolutional layer. So I'm going to call it conv1. So this is just a convolutional layer, okay? You put a convolutional layer there, and you have all the specifics in the slides, and I'll show them to you in a second, of the dimension of the filter and everything, of the details of that convolution. So you start with a convolutional layer. Then after, and you'll see people usually writing this as just a square. So obviously here there are multiple nodes and edges in that square, right? That defines this convolution. And remember, that gives us, so you have the input image x, right? The vector. And then because you do potentially many convolutions, you end up with a tensor, right? At the output. All right. Then after that, you have max pooling. Am I right? Yeah. So max pooling, let's call it max pooling 1. And now remember, max pooling, I just use this to simplify my output, right? To reduce the size, because when I convolve the image with multiple filters, right, that end up with a large tensor, right? And if I keep doing that layer after layer after layer, at the end I'm going to have a huge representation, which I don't know what to do with, right? So could you use PCA, ICA, and others to do this? Of course you could, right? Max pooling seems to work, so that's what people use. Then normalize. There is a norm 1. There is a layer that normalizes the data. Then after that, you do another convolution, another convolutional layer. And after that, you do another max pooling. Okay. And then after that, let me continue here, right? So I'm going to go down here, but that should be on top. Now, after that, you normalize again. And after that, you do another convolution. And after that, you do another convolution. Why not? And after that, anyone wants to guess? Let's try another convolution. And so on. So now you do a max pooling. And after that, you have 3 fully connected layers. So I'm going to call this 6, 7, and 8. And that's it. Right? It's that simple. All right, so I'll show you more details in the slides. But basically, you just keep putting these things together, right? And you put them together in a way that it gives you, so what we're going to do, we're going to combine these 3 things that I have shown here, right, in a layer. I'm going to call this a layer, right? So I'm going to combine this into a way that this module that I have defined is going to find me a layer, right? Then I'm going to have these 2 here plus this 1 here. I'm going to call it, this is going to be layer 2. This was layer 1, right? And this is 3, 4, 5, right? These 2 combined is going to be 5, 6, 7, 8. So 8 layers in total. Okay? Now, the most costly with respect to the parameters of that network, because obviously this network is huge, as you can see, right? Each of these layers has a lot of nodes and edges, but most of the edges are going to be right here in the last 3 layers. This is huge, right? And so the number of parameters in this network is about 50 million. 50 million parameters. It's insane. Okay? So that's why it was so difficult to train these networks, right? Even more so back then, because training 50 million parameters, even when you have tons of data, is really hard. So initialization mattered, everything mattered, right? And thus. So after this, what people started to wonder is, after this was published, it was shown that this performed really well on Imagenet. People wondered, why does it work so well, right? And so some people said, okay, what happens if I take this last layer out and I retrain the network without that layer and just try? And it turns out that you don't lose much by just taking that one layer, that one fully connected layer. You lose probably about 1% accuracy or 1.5% accuracy. What happens if I take the next layer? Then maybe you lose 3 or 4 or 5% accuracy, right? But you don't lose that much. How about if you start taking out the convolutional layers, right? Then if you take 3 convolutional layers, you see that there are 3 convolutional layers, one after the other. If you take this out, then accuracy drops like by 30 or 40%. Like, whoa. So convolutions in that problem seem to be very important. And the depth of these convolutions seem to be very important, right? So after that, people started to build systems that had even more layers than this. Okay, so let's see what happened. There's an extension of that before I get there, which is basically an extension of AlexNet, which is called ZNet, that you may want to look at, which is very similar to AlexNet, but when people were testing all these different things on AlexNet, they found out this one that it's very similar but works a little better. So after this, another network that took that idea of increasing the number of layers was VGG. And the idea of VGG is what I'm going to do, I'm going to reduce the size of the filters of the convolutions of AlexNet that were pretty large. I'm going to reduce that size of the filters, but I'm going to add a ton of layers. VGGNet started with 16 layers. So from 8 to 16, that's twice as many layers, okay? The convolutions are in VGG were very small, 3 by 3 convolutions. Okay, so very tiny. The stride, remember the amount of pixels that you move at every time that you do convolution was just 1, I think. You have the details in the slides. And also had the max pooling layers. But by doing this, let's see, they created a network. I don't have it here. If I'm not mistaken, and we'll look at the slides in a second, but if I'm not mistaken, this went up to like 100 million parameters, something like that. Huge, right? Absolutely huge. Maybe 120, 130? 130? Okay, so 130 million parameters, if I'm not mistaken, yeah. Thereabouts. Maybe a little more, a little less, but thereabouts. Okay. Now, this turned out to work really well. But look at this. We went from 50 million to 130 million. Yes, we've increased the number of layers. We've reduced the convolution, the size of the convolution, to keep things under control. But we ended up with 130 million parameters. That's just too many parameters, right? So the next step was, how can we keep this type of architectures that have more layers, or even increase the number of layers, without increasing the number of parameters? In fact, we want to reduce the number of parameters, because that makes this number of parameters just makes training a nightmare. I've been talking for 2 lectures on how difficult it is to train these networks. Well, this is really hard. 130 million, 140 million is really hard. So this is a really hard problem. So what happened next was someone came up with the idea of what's now called, well, was called from the beginning, but people call the Inception Module. So in the same sense that you had defined modules like this, right? Now we're going to define a different module. So I'm going to call this the Inception Module. And here, the idea is that you're going to take a convolution. Okay, let's see. So you're going to take the input from the previous layer. Okay. So at the very beginning, it's the input, the X, right? And then the input of the first layer, and then the input of the second layer, or the output rather, excuse me, the first layer, the second layer, and so on. And then you're going to do 1-by-1 convolutions here. You are going to do another 1-by-1 and a 3-by-3 max pooling. And let's see, what else? Then this you're going to send to a 1-by-1 convolution, and this to a 5-by-5 convolution, and this to a 3-by-3 convolution. Okay? So you take this one here, here, and here. This goes here. And this is going to now be combined in a concentration, let's call it, as the output of that module. Okay? Now, in some versions, you don't have this 1-by-1. This is a 3-by-3. This right here is dimensionality reduction, right? But instead of using max pooling here, you're going to use 1-by-1 convolutions to reduce the size of the data that you have. And here you're going to do max pooling, and then you're going to go back to 5-by-5 and 3-by-3 convolutions. Okay? And now the idea is that you start stacking this one after the other. Okay? And I'm going to show you in the slides now in a second how you stack these things together. But by doing this, they were able to reduce the number of parameters to 5 million. Okay, which is huge reduction. From AlexNet, this is a 10-time reduction, right? An order of magnitude. And from BGG, it's 20%, right? 20 times, excuse me, right? Huge reduction, absolutely huge, enormous. And the first time that this was put together by a group at Google, they call it GoogleNet. Jeez. Okay. So let's see if we can look at this on the slides. Okay. Come on. What the hell? Okay, I lost my computer. All right. Okay, so this is AlexNet. Okay, these are the different layers. So this is the image. This is an image. This is the input. These are the filters that are applied to the image over here, and that gives you the first tensor right here. Max pooling, tensors, convolutions, max pooling, convolutions, max pooling, and fully connected layers, right? Okay. This is what you observe after the convolutions, after training. After training the network, you observe the convolutions have learned to represent basically, as you can see here, type of gabord filters, right? The first few rows. And then some color information plus some other gabords, which is not a surprising fact. I mean, you're just doing a convolution after all. I've done an image, so what do we expect to get? Also, if you take patches of the image, right, of a large number of images, and you just compute the PCA of these patches, do you want to guess what your eigenvectors are going to represent? If you reconstruct these eigenvectors as images, as you did with eigenfaces or eigen cars, what have you, you're going to observe this, same thing, right? I mean, these are the basic statistics of the image when you use these equations. So with this, in the competition, the best methods that we had at the time had an error. This is error, classification error of 45% in top 1, about 28, 25, top 5. Top 5 means that you count it as correct if the algorithm gives you the correct answer within its first 5 options, right? So you give the algorithm 5 options. So, okay, I think it's a chair. If not a chair, maybe a table. If not, maybe it's a horse. And if not, maybe it's a car or a whale, right? I don't know. And if the right solution is one of them, then you count it as right. But even then, they were at 28, 25%. This went down to 37 and 17, which is pretty significant. You rarely see something like this. So this is huge, as you can see, this network. This is the Inception module that I have described. This is without the reduction, the dimensionality reduction that I have here in this row. And this is the one that we have drawn on the board. And this is the actual GoogleNet. And I had to put it sideways. So you have to read it like this, I guess. But this is the input, right? And it goes in that direction. And these are Inception modules, right? One after another, one after another, one after another, one after another. And at the end, there's just one fully connected layer, just one at the very end. You see it? The very end. Now, note something else that they did. that I've mentioned before. They took the output at this layer, they added two fully connected, and created a classifier here. They took another output here at this layer, two fully connected layers, built another classifier, and then just combine these outputs of these three different classifiers to determine what object you're looking at. Okay? Remember combining classifiers that we discussed early on in the course? So that's what I meant when I said that people use that in deep networks. It's rarely done in practice, but when you participate in competitions, you want to do everything that you can, so people play these games, right? So let's see. So here are the results of the top five error, right? Say in 2012, before deep networks, people were getting 16% and 15 in 2012, 2013, 11. In 2014, we've seen that went down to 7%. And now with GoogLeNet, it went down to 6.6%. Top five, which is pretty decent, right? I mean, we're getting into the decent range, right? Still top five, right? Not top one, but this was already a big improvement. Now, most people call this now, I think, Inception version 1, because this GoogLeNet uses its Inception. There are many versions of this Inception network, right, that have kept getting better and better, right, at this particular task, of course. All right. So let me go back here. All right. So let's see some other architectures that were proposed after this. The next thing that really, the next big thing that really came out, which is called ResNet, was the idea of proposing a different module, and you'll see that this is a recurring trend, that people come up with modules that you can combine that then lead to surprisingly good results. And the basic idea here is that you start with the previous input, or the output of the previous layer, let's say. And then you put this through a convolution. And then you do a ReLU. And then you put this through another convolution. But now you also take this previous value and you make a connection to the output of this layer. You do an addition here, you combine these two, and then you do ReLU. Okay? And that's your output. So basically, if this is x here, and this here is f of x, then this up here is f of x plus x, right? And the idea is that if the network learns that this step here is not necessary, you can set, or the network can set all these weights to 0, eliminate these layers, and you still keep the information over here, right? So we can automatically delete redundancies or parts of the network that are necessary. This module is called a residual module or block. And then there is Inception version 4, which is a combination of the Inception layers of the GoogLeNet that I have mentioned there and the general architecture of this network. So this is pretty much like a GoogLeNet plus a ResNet, combining both ideas into a single network. Okay, so let's go back to this. So here in the slides, you have the ResNet module that I have shown you in the board. And this is the ResNet right here. So you can see this jump ahead that I have drawn here, right? It is right here. There are some pooling layers added, right? And that would be the equivalent network, but without this additional residuals, okay? And this ResNet, it's compared in this figure with BGG that had 19 layers, right? Just for comparison purposes. So you can see the massiveness of this network. This is absolutely enormous. This network is crazy. Now, with this network, let's see, right here. So this is ResNet 18 or 32, depending on how many of these modules you want to use. And you can see here the training error, which is shown with the thin line, and the testing error, which is shown in the thick line, okay? And this is for top 1 error, 10 crop testing. And you can see this for the 34 going down the error, right, to about this point right here. And I have, oh, here it is. And here we have summarized the most famous architectures, which I have talked about today, from the LeNet, which was proposed in 1998, which had about 60,000 parameters. So it looks silly right now. Only had 2 convolutions and 3 fully connected. To AlexNet that went into 50, 60 million parameters, 5 convolutions, 3 max poolings, 3 fully connected. VGG jumped hugely to 13 convolutional layers, 5 max pooling, 3 fully connected, a massive 138 million parameters. GoogLeNet or Inception 1, which has 21 convolutions, 5 max pooling, 1 average pooling, and 1 fully connected, with version 1 just having 5 million parameters. That's what's really good about it. Version 3 went up to 23, but still, compared to the original AlexNet. And then the ResNet that I've talked about last has a very small number of parameters compared to these early ones, 25 million. And it has 34 convolutional layers, 34, one after the other. Just absolutely massive. It's insane. So here in this plot, you can see the top 1 accuracy on Imagenet, right, as time went by. So AlexNet started at top 1. This means that it has to be right in its first guess, right? You only have an option to get it right. It wasn't even at 55, right? It was shy of 55%. That kept increasing a little bit. GoogleNet when getting closer to 70. ResNet jumped this to about the 70 range. VGG went over 70. And then after that, the big ResNets kept getting better and better. And Inception 4, which remember it's a combination of the idea of the ResNet module and the Inception module, went over 80% accuracy, which is absolutely extraordinary. And then here in this plot, what you have, it's an x-axis. Here in the x-axis, it's showing the number of operations that are required for each of these networks. Okay. The x-axis is the top one accuracy that I've shown here on this left plot. And the size of these circles correspond to the number of parameters that need to be estimated in each of the networks, right? So AlexNet was very large, as you can see. GoogleNet, very small number of parameters. And even though it was much smaller, it performed much better in accuracy terms, right? And then what I want to show you here, which I think is very important, is that as networks grow in size, right? You see the size of those networks, especially VGG, but even these ones, Inception 4, ResNet 152 layers. You can see that they perform better than Imagenet, but not much better, right? This is starting to saturate. And this is important because when all this started, the idea of deep networks is not that they are necessarily the machine learning algorithm to go. Many algorithms are important, and many algorithms are used for a variety of problems. It depends on your problem. But for many of the algorithms that we have described here, like support vector machines, maybe to a lesser degree, but also KSDA, and especially Gaussian mixture models because of the limitations of the EM algorithm. As the amount of data shown here in the x-axis, as the amount of data grows, these algorithms shown in blue, performance on the y-axis, these algorithms perform better and better and better, but then after a certain amount of data, they start to saturate, right? Doesn't matter that you have more data, the algorithm is just saturating, and that goes back to our VC dimensionality, the capacity of these algorithms that we briefly discussed. Deep networks, because they have a great capacity to learn, but also because of the optimization methods that we can use for gradient descent that I've spent so much time talking about, they can learn from more data, right? So the relevance of deep networks has come about because of big data, right? Without big data, we wouldn't be talking about deep networks today. We'd be still talking about other methods that I have talked about in class. So if you have big data, if you have a lot of training data, in supervised learning especially, then yes, deep networks don't saturate as fast as other algorithms, but they also saturate, right? I don't want to give you the impression that they don't saturate. Of course they saturate. Every algorithm saturates. And this is shown here, right? It's reached a point where the algorithms start to saturate, right? It doesn't matter, you keep making them larger, they start to have problems. Okay, here is an example of a network working on face recognition, and some people call this deep face. And that basically this is the same thing. You start adding certain number of convolutions. At the very end, you add maybe a fully connected layer at the very end to do classification. And then compared to human performance, this was one of the first algorithms, not the first, but one of the first algorithms that was as good as humans at specific face tasks that used a data set that's called labeled faces in the wild. All right, any questions? Before I move on, no? You sure? Okay, so let's move on with more networks. So There are a variety of other networks that are not as known, but they're out there that at least you should be familiar with. And most of them are either implemented in these packages that we have given you, or you can find them in some online, freely available online in some platform. For example, other networks that you will see out there that people use, one of them is called Fractal Net. And that gets rid of the residual step, right? Eliminates the residual step that we have to find in ResNet, and substitute it instead with a combination of low and high layers. So the idea would be to do something like this. Let me do it from the top. So if this is my input, right? I'm going to go in this direction now. So I'm going to have my layers here, right? So let's say they have something like this, for example. Okay. Let's say I have something like this. And then after that, so this is my module. And after that, I add this module again. So I'm just going to repeat this. Right? And I can repeat this as many times as I want. But then what I'm going to do, I'm going to take this input here, and I'm going to process it here. And that output, I'm going to add it here. You see how this works? And now if I do this again, so now I do this, this, and this. Now, what I'm going to do, I'm going to take this again here, right, like I did here, and combine, or actually, my bad, down here, and then combine this, right, into the next. But I'm also going to take this one here, I'm going to compute here, and also combine this one, right? And that's similar to the idea of the ResNet, but instead it just keeps the depth of the modules here, but a simpler version of that here, right? At every level. You will also see others working in what they call dense nets or dense CNNs. This is another type of architectures, and the idea is similar, right? So if I start with my input and I do a convolutional layer, and after that I may do max pooling or normalization, batch normalization, but I keep doing convolutional layers here, right? Which, remember, this is what seems to work. Then what I'm going to do, I'm going to have this input in here, but I'm also going to send this input here. I'm going to send maybe this input here, and I may send then this input here. Oops, not this one. Makes some sense. This input here, and this input here. And then I'm going to take this one, and here, and so on. You see how this goes? So you keep adding connections over and over and over again. And these type of networks, this one, but especially this one, are only possible if you add batch normalization. If you don't batch normalize, you don't add batch normalization, you're not going to be able to learn. That's just insane. All right, another type of network that people use, it's the dilated residual network, or ResNet. And the idea here is that reducing the resolution of the original image may actually help, and that can be done as a set of smaller convolutions, as I've mentioned in Inception as well. And this can be done with the help of what's called a dilated convolution instead. So the idea is to substitute the regular convolution by what's called a dilated convolution. The advantage of that is that you can achieve comparable results to ResNet with a much smaller number of layers, which is always welcome because it's easier to train. Okay. What else? The other type of networks that are important to know, they are called recurrent neural nets. And these are actually important. There are a lot of important applications of recurrent nets. And the idea is that until now, as you have seen, all I'm doing, I'm building modules, right? Layers, and then I'm combining them feed forward, right? I use this feed forward architecture. But why should I stop right here? There are many other types of architectures I could have. For example, I may have an input here, right? And then I'm going to process this here maybe, then I'm going to process in another layer. But now what I'm going to do, I'm going to add additional layers sideways in this direction. And this is going to allow me to get more outputs than inputs. Okay. But you could also do it the other way around. You could, so this would be all outputs, out, out, out. But you could also say, I have multiple inputs. In. And now what I'm going to do, I'm going to combine this laterally as before. But now instead of creating more outputs, I create less outputs, right? So I reduce the number of outputs. Now, when I do this right here, right, I go from a larger representation to a smaller one. This is the same thing that we did with many other algorithms. This is called generally an encoder. Right? And this may be called, in some instances, it could be called a decoder. Now, of course, no one is stopping you from doing something even more interesting than this and having multiple inputs and multiple outputs. So let's see this. So for example, one could have multiple inputs here. So let's say in, as before. So I have these multiple inputs like I had right here. And now I'm going to combine these laterally. OK. And this is going to be my out. So like here, this has nothing has changed yet. But now I'm going to add this as well. So I can have now more layers laterally and then more outputs. and so on. You can build these structures at will, however you want. And the idea is that of a recurrent neural network is that you don't have to draw things like this. You could just say, I have my input layer. I have my recurrent neural network, whatever that is. And then I have my output. And what happens is that I take this output here, and I use it as input, right? OK. So here, I take that output of the network, and I input it in the next, which is the exact same thing as this, and then in the next, and then the output, right? Take the output. So this is the idea of a recurrent neural network. Basic module block that you can design, or some people call them cells as well. So a module that you can design is take xt, which is the input or the output rather of the previous layer at time t or at layer t. Then take the lateral, so this would be xt here. Then take the take the lateral that's coming from the previous one, so ht minus 1. So I'm going to take this ht minus 1. Now you combine this somehow. So here you have to combine this, for example, stack them together. It's a classical solution. You have the weights of the layer, right, which you are now going to use to perform some computation here, right? And then you have your activation function, maybe a ReLU. Typically, recurrent networks use 10 each. And that gives you your HT, right? And this right here is your module, right, or block or cell. And you can write this, if you like, as f, your function that you're performing here, right? F of h t minus 1, which is my input right here, right? And ht, and then maybe your parameters w, right? You see how this works? Okay. So you take your inputs, right? xt. G. You take your inputs, ht minus 1, xt, the parameters, and you output. This output would be ht for the next module as a next input for the following module, or the output of the network. Some people use the same weight matrix for all the modules. Some people like to have specific parameters for specific modules, but most people just use the same matrix, same parameter matrix, W, okay, just to make things easier for training. Now, obviously, to compute here the output, how well you're doing, you're going to have Li, Lj, Lk, right? The different loss functions that you're going to use here. And then your general loss is going to be the sum over all I of all the losses that you compute in each of the outputs, right? So this has many applications, obviously. You could have an input here that provides you automatically multiple outputs that are of your interest, right? So for example, I could give you an image here, and you will see this done a lot. And you could output I'll show you, I'll do this on the board, but you could have an input here, just an image, and then you could output a description of that image, right? And each of these outputs could be a keyword or a part of a sentence, okay? Here, maybe you're inputting a video instead of an image, right? So a video, it's a number of images. So you input number of images, which is a video, and you output, say, the action that is being performed by the person or the object in that video, right? And so on. Now, training. Here, there's a problem because there is time, right? Because this thing is recurrent, so you process this information, then you go back and you process it again, and then you go back, right? Because it's recurrent, you cannot use the exact same backpropagation, so you need to use something that is called truncated backpropagation. And that simply means that we trained a set of consecutive hidden states at each time, okay? Now, if you want to do this, this truncated backpropagation is also included in all these softwares that we have mentioned, right? In PyTorch, there's a function, mean something RNN. No one remembers the exact name? All right, but there's a function that does this. I'll post it in Carmen for you in Python. Okay, so let me give you this example very briefly of image captioning, which is a classical application of this model, of this architecture of network, rather. So the problem here is you're given an image, okay? You're given an image, and the goal is to provide an automatic captioning of the image. So here I am. I start with my image. Okay. Now what I'm going to do, this is how these things are built. So for example, I give you an image of a mom and her daughter eating at the dining table, right? And I want the caption to be mom and daughter eat at the dining table. That's a caption I actually want, right? So I have a lot of training data. I have images that I have manually annotated with sentences myself, with captions. And now I want network to train to do that automatically. So the very first thing that I'm going to do, I'm going to use one of the CNNs that I've talked about earlier, right? Say ResNet, Inception version 4, whatever, right? Whichever you want. And I'm going to train this, say, with Imagenet or some big data set of images. All right. And the output of that network is what I'm going to use for the ResNet. And now here, I'm going to have my ResNet, RNN, ResNet, excuse me, my recurrent network. And then this is my input. And that output is going to be re-inputted in my network, right? And this is going to be the output of this network, going to give me the first word. Right? This means that I'm just passing through the information of the CNN through that network. And the output, I take it here. And now I take this word that I output here, and I input it here. And that's going to output my second word. Okay. And I keep repeating that. And I keep repeating that to infinitum until I decide to stop. Okay. So the way this is started, people will just write the word start. And that just tells the network that word means I need to start outputting information. Okay? And the words will be output until the network outputs the word stop. When you see stop as the output, means it's done. Okay? This looks completely insane, I know. So this goes on. The function, the h function that I've defined over there is the 10h. As I said, most RNNs use 10h. And you use the weights with h, xh, and the input, right, plus the weights hh times h plus the weights ih times v. And I'm not going to get into details because we're running out of time, but you have the paper also in Canvas. So if you're interested, look at this. But basically, once this is already trained, right? This is pre-trained with Imagenet or some data set for images. And then you train this with this backpropagation I just mentioned. And if you have enough training samples, right, meaning that I have images that I have manually annotated or I have captioned manually, this can actually learn relatively well, and it gives decent results. Now, once in a while, it gives results that are so funny, maybe even insulting, so you have to be careful. But there are some results that are completely insane, right? That make no sense. But it works better than you would expect, right? This actually learns. It's actually pretty amazing how these things work. Okay, so how are we doing on time? Oof, okay, a few more minutes. Okay, so an extension of this that I want you to be aware of as well, it's called a RNN. And this become more and more popular, actually, in recent years. It's been applied to other types of networks. RNNs with an attentional module. Okay. So what this is that when in computer vision specifically, but also in translation and in sound, especially when you interpret the speech, right? These algorithms do not look at all the pixels in the image to make their determination of which word or which class they have to output, right? They specifically look at some key areas of the image that have information that correlates with the output that you want, right? And the attention module is designed specifically to find out which area of the image is the one that's giving you that specific output. Okay? See this? And the thing is that you can train these things simultaneously. You can train the attentional module and the network, and that actually makes things work better. So the way that would work is that as before, right, I have my image here. I have my CNN. And then what I'm going to have here is I'm going to build my attentional module here. Then this is going to go to my RNN, right, H1, all the way to whatever I have. Here I'm going to have my output 1, my output 2, and so on. And this I'm going to send back here into the attention. And then this and this is the key now, this is going to be described as a latent space, Z, okay? My Z variable. Remember Z variable, the latent space? And this is just nothing else than a representation of what I have right here. And then this Z value is going to be another input to my RNN, okay? Right? So that this network, when it learns, it first learns like I was learning here. But then when it's learning, it's sending that information backwards, telling this module, what am I looking at? This creates a latent representation of this that is sent back to that module, telling all the other modules, this is the information that we're looking at. Do we need to change this or not, right, to make it work? Do we need to, instead of looking at this area, look at this other area, right? So by combining these two things together, the network learns to look at different areas, specific areas that work best for it. So I have actually a lot to say about this, but we don't have time. But I'll try to, I haven't posted any papers on this, but I'll try to post some papers on this. It's pretty cool. All right, a couple more things. And this will be the last couple things for today. There's just so much to cover in deep networks for two reasons. Number one, there's been a lot of progress in the last 4 or 5 years in this area. But second, one of the reasons is that we don't really know why these things really work, right? So all we can do is tell you, these are the things that have been done and the things that do work, rather than giving you the reasons why things work and let you design anything that you want based on those laws, right? We don't have the Newton laws of deep neural networks yet, but active area of research, obviously, you can imagine. All right, more about this. There's a multi-layer version of RNNs, obviously. So in that case, you have the module is going to be your input here, and then you're going to have this HT layer 1, HT layer 2, and so on, right? Up to HT layer capital T, let's say, and then this is going to be your output, right? And you can define this formally as my HT at layer L. It's the 10H of capital W at layer L and multiplied by HT at layer L and L minus 1, right? Now, typically people will use 2, maybe 3 of these layers. After that, it just becomes increasingly impossible to train these things. I mean, they're just too massive, right? Just too many things. So optimization is a big area of research right now, right? Which is not specifically machine learning. It's just becoming more and more important in machine learning. So people are working on optimization because optimizing these huge networks is increasingly important and increasingly difficult. Okay, and the last one that I wanted to mention is the long short-term memory network. So last one for today. And these are most typically called LSTMs. This became really popular when RNNs came along. This became very popular, which is funny because this is a network that was presented in a paper back in 1997. And all of a sudden, there was a resurgence of interest in this network. And the reason is because the way it's structured does not have as much of the problem of vanishing gradients that we have seen before. We saw in the last lecture, the last couple lectures, rather. That problem is not very prevalent here, right? It's actually almost non-existent. It's much diminished. So they become extremely popular for a while. And now they're losing their allure, I guess, a little. But still, I think are very useful networks to know about and to work with. All right. So, and the reason this is done is because the matrix W is always guaranteed to have an eigenvalue smaller or equal than 1, right? So the way that they control the size of the weights and therefore of the gradient. So this has this module, this LSTM module has 4 different outputs. They're called I, F, O, and G. And they stand for the input gate, okay, the I for input gate, the F, the forget gate, the O, the output gate, and the G, the 10H gate, okay? And now the way this works is you use, for the first 3, you're going to use a sigmoidal function, a logistic sigmoidal, okay? So you can just write sigma, maybe, for simplicity. So, and the last one, as I said, is going to use the 10H, okay? And then you have the weight matrix. And then as before, where do I have this? As before here, right? You multiply this by HT minus 1 and XT, okay? Oops, that should be subscript, sorry. T minus 1 and T. So you can say that I'm going to compute CT as an intermediate step. CT is F product with CT minus 1. Now this means a product of element by element, right? Non by element product. Plus I product with G. That's called the state of the cell. And then HT, which is going to be equal to O, this one, the output, product with 10H of CT, okay? And these are the 2 hidden states of that module, if you will. And if you want to draw, people like to draw these modules. I've seen a variety of drawings of this. There's none that is totally convincing, but maybe this one is one of the best that I've seen out there. So you can say HT minus 1, W, and CT minus 1 here. Then you combine this, stack it together, right, with XI. And then you you multiply with W, and then you generate the outputs here, which are they O, G, I, and this here F. This one and this one are multiply, and then you add them together with these 2. And then CT, and then this is going to go to a 10H, and you take the O, multiply it by this, and this is your HT, right? So you can see it's a kind of a mess. That's why it's difficult to draw this module, right? But the equation that you have on the right is much easier to interpret, right? Sometimes it's actually surprisingly, sometimes it's easier to understand the equations at the drawing, and sometimes it's easier to understand the drawing than the equations. All right, the last type of networks that we're going to cover in our final lectures is going to be generative models. And this is potentially the most exciting area right now in research. So there's a lot that's been happening in the last just couple years. Huge amount of papers, very interesting results. So I'll try to summarize this. I have a few more things to say about all this that I've said today that can be summarized in a few minutes. But then after that, I want to talk about generative methods. And this generative method is our best hope to move to what we call, as I've said many times, unsupervised learning, right? So everything that I've done thus far in deep networks is supervised, right? You need to have not only the X and Y's in your training data, right? But these X and Y's, remember that we always have our training set. It's xi, yi, right? The input and the output, I1 through n. That n has to be really, really large in deep networks. Otherwise, you're not going to be able to estimate 50 million, even 5 million parameters, right? I mean, it's insane. So generative methods are a big hope for being able to someday going fully unsupervised, right? So that you don't need any data or very few data at least. All right, so we'll talk about that next.